One of the ways we have of differentiating types of differential equations is by talking about the order. And by the order of a differential equation, what we mean is the order of the highest degree derivative, or the degree of the highest degree derivative involved in that equation. So the example we did last time was that 6y plus y prime equals y double prime. This is a second order differential equation because it involves a second derivative. We're actually going to spend most of our time talking about first order differential equations, largely because there's a lot that we can still do while not worrying about second or third or fourth derivatives. So one example that we're going to work with is, well, what if y prime, what if our derivative is some expression in terms of what the actual value is? Okay, so we're going to look at a lot of different first order differential equations. The first one we're looking at is this one, which comes from this example down here. The setup is that we're talking about modeling the population of deer in a forest, right? And we're sort of past the point where the dominating effect is how many deer and how many, deer babies they can have. And we've moved on to, all right, what's sort of the carrying capacity of the forest? Like how much room is there, how much food is there? And the setup is we're saying, all right, the growth rates, so the rate of change in the population, so this is births minus deaths, is 100 minus the current population. In other words, we're saying it's the same differential equation, but I'm going to write it as if y is our population, the change in population over the change in time is 100 minus that population. Okay, and again, we're going to talk more in a little bit about how we can solve this, but I wanted to point out what solutions to this look like. And so the solution to this differential equation is going to be the collection of functions of the form 100 plus some constant e to the negative t. And you can check this just like we checked the other ones. You could take this derivative and see that the derivative of this is 100 minus the function itself. Right. But I want to talk about what these different functions look like. So if we have our population, so the point is that this function is supposed to model how many deer are in the forest as time goes on. So if we start at, and notice that we have this constant, c up front, which can be anything. There's this is an infinite class of functions, any one of which solves this differential equation. So this has to do with choosing what our starting point is. If we choose a c that includes, let's say, this point, let's say 100 is up here, then if we plotted this function, it's 100 plus this, it's going to look something like this. In other words, because the carrying capacity of the forest, or the maximum number of deer that the forest can sustain is 100, the population is going to be approaching this 100 number, but never quite actually getting there. This actually comes from a c of something negative, so let's say c is negative 200. The different c's are really just different ways of specifying which particular curve we want to talk about. If we talked about a different function, I believe this is something like c equals negative 100, we're going to get a different looking function, but it still has the same relative behavior. So depending on how many deer are in the forest at our starting point, let's say this is time t equals 0, depending on how many deer start there, we're going to, the model is going to look a little bit different, but have roughly the same type of behavior, right? One other question we might ask is, let's say maybe started with 70 or 20. What if we started with something like 120? Well, if we were to plot this function, specifying a certain c, I believe c equals something like 50 works for this. This is an approximation, no actual numbers involved. Then our model is going to look like this. Because the forest only really has the carrying capacity to support 100 deer, if we start off with more than that, the deer are going to sort of start dying off until we get down to that carrying capacity population.